This is Algebra 2 with trig, 6b.2. We are going to graph logarithmic functions. So looking at some converting logarithms into exponential, which is a skill we're going to need to graph, let's look at this one. The base is 5, and you know a logarithm equals the exponent. So to convert this to exponential form, this is going to be 5 with an exponent of 3, and that equals 125. So you can take a logarithmic form and write it in exponential form. They're still equivalent. This doesn't have a base written. So when the base is not written, that means it's a 10. So this is 10 to the 5th power equals 100,000. Now for evaluating, we're going to evaluate what this would be. Really what you're asking yourself is 15 to what power is going to equal 15? 15 to the 1st power is going to equal 15. So this is going to equal 1. This one's a little bit more confusing. 3 to what power equals 1 over 27? Well, you know that 3 to the 3rd power equals 27, but you need the 27 in the denominator. So 3 to the negative 3rd. Negative 3 is going to put your value in the denominator and cube it, so you get 27. You might like to take the same rule we were doing before, write this as exponential. 3 to the x equals 1 over 27. We can write this without a fraction form. We see we don't have two fractions. So let's get rid of our fraction. So that's 27 to the negative 1 power. So essentially I've taken this fraction and flipped it upside down. And now I have 27 over 1. We just don't usually write the 1. And it's to the negative 1 power. So it still has the same value as 1 over 27. Now I notice my bases aren't quite the same. I cannot turn a 3 into a bigger number, but I can turn the 27 into a smaller number. By saying 3 to the 3rd power, that is 27. The 3, the exponent's going to multiply the negative 1. So that's going to be a negative 3 as an exponent. That gives us 27 with a negative 1, which puts it in the denominator. Now, since my bases are the same, I can just set my exponents equal to each other. There's no more solving we need to do. So to evaluate this, you might realize that 3 to the 3rd power is 27, so it has to be a negative 3. Or you can set it up in exponential form and get bases the same and use your exponents to equal each other. Different ways to handle it. To talk about graphing, some of those same skills will be used in graphing. First of all, the graph of a logarithm is shown below. This is when b is greater than 1. There's the logarithmic graph. This is kind of close to y equals log base 2 of x. And this one looks pretty close to y equals 2 to the x. So this is your exponential form. And if we reflect it over the line y equals x, then we get our logarithmic form. Notice this one. This is exponential decay. So this is close to y equals 1/2 to the x power. You go from 4 down to 2, down to 1, down to 1/2, down to 1/4. So it's exponential decay. This graph here is y equals log to the 1/2 x. So here's your logarithmic graph. Notice what used to be positive y or positive x values. Positive x values was an asymptote. Now we have positive y values as your asymptote. Over here, it used to be negative x values was your asymptote. Now we have negative y values is towards your asymptote. It's approaching over here. So it's just reflecting across. So now we have the y-axis as our asymptote. So that is x equals 0. That's our vertical asymptote. The domain of our logarithm is now going to be what the range was. If you remember your range of your exponential, that's going to be the domain of the logarithm. Take a look at the graph. If you have an asymptote here at the y-axis, all the x values are to the right of it. So it's x is greater than 0. In interval notation, that would be 0, infinity, with rounded brackets on either side. Now, what would our range be? Everyone should try to come up with an answer. Everyone's thinking. Take a look at the graph. The graph clearly drops down forever. It'd be better if there was arrows written on this, because it does go down forever. And slowly but surely, this is increasing upwards, and it goes up forever. So if it goes down forever, which clearly it does, it goes up forever, we're going to have a range of all real numbers. And you can use the abbreviation to represent that. Interval notation would be negative infinity to positive infinity. So we're going to use those concepts to graph our logarithm. The first thing we want to do is write it in exponential form. This logarithm we should write in exponential form. So to do that, we take our base. We know the logarithm equals the exponent of the x. So it equals, our exponential is going to equal the x. These are still equivalent. This is just exponential form. This is logarithmic form. So we're going to make a table, and we're going to use this exponential form to help us create the values in our table. Now we're going to choose values for y. We typically choose values for x. But in this case, if you choose values for x, then you had to do math to try to figure out how the y was going to match to the x, and did you choose a good x for it to try to match? It would be tricky. But if you pick values for y, we can just do the calculation, and that is just clearly x. So let's do -1, 0, and 1. We may try some other ones after that. So what do we get for the x value when the y value is -1? So what is 2 to the -1 power? It's going to be 1/2. The negative exponent tells us to put this put this value into the denominator. What is 2 to the 0 power?
1.
Any number to the 0 power is 1. What is 2 to the first power? That's pretty clear. Whatever your base is to the first power is going to be 2. Whatever your base is to the 0 power is going to be 1. Whatever your base is to the negative 1 power is going to be the reciprocal. So we can plot these out. Now, be careful. Don't do negative 1 a half. You got to do the x is a half. X is a half. Y is negative 1. X is 1. Y is 0. X is 2. Y is 1. So let's continue this a little bit more. If the y value was 2, what would we get for x? 2 squared is 4. So when x is 4, we're up at 2. Let's do one more. When the y value is 3, 2 to the third power would give us 8. So when x is 8, 1, 2, 3, 4, 5, 6, 7, 8, then we're up at 3. 1, 2, 3. So notice we're coming down, getting closer and closer to this y-axis. And we're pointing out towards the right. That's our logarithm. Y equals log base 2 of x. That has an asymptote, and we should put our dashed line and label our asymptote on our graph. That's x equals 0. Our domain is everything greater than that x is 0. Our range is all real numbers. There is no comparison. This is as basic as logarithm base 2 can get. So this is a parent function. So nothing else to say there. End behavior. Now listen to this. This is kind of weird. We typically say as x approaches negative infinity, when we look to the left of the graph, what happens as we look to the left of the graph? What does it approach? It's approaching 0. It doesn't get to negative numbers. It doesn't go to negative infinity. It only approaches 0. What is the y value doing at that moment as we get closer and closer and closer to the 0? It's dropping down, so it's going to negative infinity. As we move to the right, there is no limitation how far to the right we can go. So there's our positive infinity. What's the graph doing going that way? It's going to infinity. So if you look here at your end behavior, you can see your x values, which is your domain from 0 to infinity. You can see your range from negative infinity to infinity. It has your domain and your range built into it. That's kind of neat. So we turn our page. Now we're going to talk about graphing a logarithm and doing a translation to it. We're first going to graph y equals log base b of x. We're going to graph that one first. And then we're going to do our translation. Horizontally, h units, and vertically, k units. Since our asymptote is vertical, we know it's going to be an h value. And since we're going to be translating our graph right and left, that's going to be determined by h. Our vertical asymptote is an x value. X equals h. So to graph this, we're first going to graph y equals log base 3 of x. So we're going to write this as exponential form. That is 3 to the y power equals x. And that helps us develop our table. We'll first start our table out. We're doing y equals log base 3 of x. That's what we're graphing. These two are equivalent. They mean the same thing. We're going to do -1, 0, and 1. We can do more numbers if we want to. So when the y is -1, our x value, so 3 to the -1 power, is 1/3. 3 to the 0 power is 1. 3 to the first power is 3. We can continue this. Make your y values bigger. So 3 to the second power is 9. And so forth. So remember to go right and left with your x values. 1/3 and down -1. To the right 1 and down 0. To the right 3 and up 1. To the right 9 and up 2. So that's where we're heading towards. So we label our graph y equals log base 3 of x. Now we're going to translate it. We notice that our h value is 1 and our k value is 2. So we're right 1 unit and we're up 2 units. So we're going to take each one of these points and go to the right 1 and up 2. To the right 1 and up 2. Right 1 and up 2. And this is going to go to the right 1 and up 2. So we now have our equation, or our graph, coming straight through here. And that's going to be y equals log base 3 of x minus 1, and that has to be in parentheses, plus 2. So that means since we translated to the right 1, we now have our asymptote that is also moved to the right 1. And you want to label that on your graph. So the asymptote is x equals 1. We know our h value came from our equation. That told us how to translate it. So our domain is now from 1 and getting bigger. It does not include 1. We're putting the domain of our final graph. Our final graph has a translation. Our table does not have the translation. Our range would be all real numbers. Our comparison we can compare it off of our table. We see that the graph went to the right 1 and up 2. There is no stretch, there is no reflection. Okay, our last one. To graph here, this is supposed to be your turn. You're supposed to be able to do all these. But I'll move you right along. You can pause the video. You can try it. Let's do that. We'll pause the video and you work this one out. So we're going to write this as y equals log base half of x. And we're going to write that in exponential form. A half to the y power, logarithm equals the exponent, equals x. So when we do our logarithm, y equals log base a half of x, we're going to pick values for y. Now I'm going to leave us a box just to come back to -1, 0, and 1. So when y is -1, that flips our fraction over and we actually get 2. When y is 0, any number to the 0 power is always 1. Any base to the first power is always that base. So if this guy got any bigger, then we'd have 1/4. Square the top, square the bottom. Over here, if we had a -2, -2 as your exponent, negative would flip it over and then square it. So we would get 4. So we can plot these. At -2, we're up at 4. At -1, we're up at 2. Oh, sorry. I did that backwards. See? You got to pay attention to your x's. Your x's are on top. My bad. 1, 2, 3, 4, we're down at -2. At 2, we're down at -1. When x is 1, we're at 0. X is a half, we're at 1. I was looking to see where the asymptote was, and it wasn't making sense. I was going forever right and left. So you can use your knowledge to try to clear up any mistakes that you're creating. So that would give us an asymptote here at the y-axis. But we're going to do our translation with h being -2 and our k being -3. So we're going to go to the left 2, and we're going to go down 3. Left 2, down 3. Left 2, down 3. And we have our asymptote at x equals -2 because this is x plus 2. We like to trace our graph out for which one is the real graph we're doing. We like to label our graph. We know our domain is x is greater than -2, and our range is all real numbers.